Hello, my name is Susan Stipp. I'm a professor at the Nano-Science Center and the chemistry department at the University of Copenhagen. And I'd like to tell you a little bit today about the research that my group does and why we're so excited about using nanotechniques to look at the surfaces of solids in nature. Here you see the atoms of water, oxygen, on the surface of a little bitty piece of chalk, like Münzklint. We investigate the interaction between water and surfaces because it has a great deal to decide about how that material functions in nature, its properties and its behavior. The water interaction with the surface can decide whether Münzklint stands as a nice cliff, solid, or whether it falls down into the sea. The interaction of water with the solid changes its wetting properties. So in my group, we apply nanotechnology to understand nature better, to learn its secrets. And then we use this new information to try to find solutions to society's challenges. And some of those challenges include ensuring cleaner water, storing waste more safely, converting CO2 from gas to mineral form so it'll be stable for geological time, producing more oil from existing reservoirs so Denmark can remain self-sufficient in energy until we manage to get the sustainable forms to an economic state. And one of the big mysteries of our world, the world that we live in, is how do organisms make biominerals? How do our bodies make bones and teeth? And how do oysters make shells? Here's Nico. He's about to put a sample in one of our instruments where we find out what is the chemical composition of the absolute surface, the interface between a solid and a fluid. And here we mean fluid can be gas or water or oil. Anything that flows is a fluid. So why surfaces? Well, all the action is at the fluid surface interface, where the fluid interacts with the solid and controls the composition of both. We've known about solids for tens of thousands of years. Our ancestors used flint for stones and they used gold for jewelry. We've known about wet chemistry and how to analyze things in solution for a couple of hundred years. People tried to turn lead into gold. They understood about what was going on in a solution. But this here at the interface, this molecular thick layer where fluid and solid meet, was completely unknown until a couple of decades ago. It's a little bit difficult to get a feel for how small a molecule really is. This is the world we live in at the meter scale. We can see down to millimeters, we can walk kilometers. You're about a half a meter away from your nearest neighbor. We understand the meter scale. The bacteria scale is 6 orders of magnitude smaller, the micrometer scale. Atoms are 4 orders of magnitude even further, 10 orders of magnitude. This is the angstrom scale. So 10 angstroms makes a nanometer. If we wanted to have a concept of this difference in order of magnitude, we could think of sitting on the moon with a very strong pair of glasses looking down on our heads. We could see our identity, we could see our structure, how we sit in the room, and we could see the relationship between us with those strong glasses. Now, it's good to have clean water to drink, and it's important to be responsible about how we store our waste. And so one question is, can we minimize the risk of groundwater contamination, of soil contamination, using nanotechniques? And the answer is yes. We study heavy metals, pesticides, organic compounds, and radioactive species. And we investigate their interaction with soil particles or treatment particles so we can see how to improve the methods for preventing contamination from reaching the places we don't want it. Now, below the water table, oxygen's scarce, and rust isn't red. Iron oxide isn't red, like on our bicycles or our cars. It's green. And here, Bo and Maria are working in an oxygen-free glove box, and here you see the iron oxide is blue-green. It looks like this in a glass, and it looks like this with our atomic force microscope. Remember that a bacterium is about 1 micrometer long, so many of these particles are smaller than bacteria. And we can think of the surface area there. The smaller the particles, the higher the surface area. And a gram, about this much, has a surface area of 200 to 400 meters squared. That's a really big apartment. So the surface of green rust has a very high capacity for taking up toxic materials. Now, green rust is very reactive, both because it has a large surface area and also because it's redox active. It has those iron 2 groups that want to become iron 3. Chromium is a toxic element, and in its 6-valent form, it's quite soluble. It can move with the groundwater. But when it reacts with green rust, the green rust oxidizes to ochre, and the chromium 6 becomes chromium 3. Now, chromium 3 is not toxic. In fact, we need a little bit in our diet or in vitamin pills. So here Lona is putting some chromium into the vessel, and here we see green rust by itself with a little bit of chrome and a little bit more and quite a bit. And you see it turns to ochre. And it's very stable there. Have you ever tried to wash the rust off your bicycle? It's not soluble, and neither is the chrome-doped rust. Biomineralization is a topic that we're very interested in because it's part of nature. It helps in the carbon cycle. And if we could understand how our bodies do it, how do our bodies make bones and teeth, then we might be able to offer some information that would help us prevent arthritis and osteoporosis, two of the age illnesses that have so far not been preventable, only treatable. Algae, like this one, are one-celled organisms. They're photosynthetic, and this is about 10 or 12 micrometers across. They make these very beautiful and elaborate calcite shells to cover their one cell with. And the question is, how can one cell make such a beautiful structure? These are some we've grown in the laboratory. These are some that are 60 million years old from chalk, like Münzklint. And the question is, how do they do it? Well, we know that they use complex sugars and proteins. Now, this is a model. This is one of our important tools in nanoscience, is to use molecular models that take the fundamental principles of physics and tell us how electrons move around an atom when they're bonded to other atoms. And we take this fundamental information, we put it into a computer, we let it run for days, hours, and months, and we get information back. And so this is a model of how the molecule here and the surface interact. This is calcite, like forms in the bottom of your tea kettle and is the main mineral in chalk. And this is a trisaccharide. It's made of 3 rings of sugar. And when you watch, oh, there's water here too, but we've made that invisible so you could see the movement of these two better. And when you see it, watch for how the OH groups here interact with the surface. Once the molecule puts its feet down on the surface, it can dance, but it can't go away again. So we can see it bonding and loosening its bond with the surface, but it never can fly away. So once polysaccharide is many, many rings of sugar. It's even less likely to leave. Once it sticks to a surface, it doesn't go. And that's the key that biomineralizing organisms use to make their biominerals. The last story I'd like to tell you about is volcanic ash. And here the question is, can our nanotechniques help aviation authorities? The answer is yes again. Here's Siggy Gislason collecting ash at noon on a sunny day, but it's completely black. He has to use the lights of the car to be able to see what he's doing. This is when Eyjafjallajökull blew a few years ago. And we got some of that ash and examined it in correspondence with typical ash. This is typical volcanic ash. The particles are rounded. They're small. There's a 100 micrometer scale bar. And they have gas bubbles inside. This is the explosive ash that came from Eyjafjallajökull when it closed the airspace over much of Europe. The particles are really small and they're really sharp. So now what does that mean to planes? Well, they're extremely fine, so they travel far. They're small, so they melt easily in jet engines. And their sharpness has an effect on their abrasiveness. They can wear on the windows and the plane wings, the paint on the outside, and that's not so good for the airplanes. But the good thing is that they're less toxic than typical ash, and that's because the volcano had a glacier on top. And when the volcano began to erupt, the glacier melted, the cold water flowed down into the magma, and it exploded. All those gas bubbles burst. So the rinsing of the water on the ash took away those salts. So the salt went in the river that ran down the volcano rather than out into the air and to fall on the fields. So that means Iceland's sheep were less affected by this kind of ash than normally. If they eat ash with their grass that has fluoride in it, then they get deformed bones and eventually die. Now the good thing is that what we learned from the Eyjafjallajökull eruption about size and abrasiveness was used a year later when the aviation authorities had to decide about which airspace to close when Grimsvötn blew. So now they know, now they can, our work and the work of many other scientists went together to make models that they could use to really know where it was dangerous to fly. So I come back to the beginning to end, and I say again, my main message is what happens at the meter, kilometer, or gigameter scale is controlled by the physics and chemistry at the nanoscale. If we can understand how nature works, we can use that information to solve some of society's problems.